Hello, lazy chemists, and welcome to today's lecture where we are going to be talking about bond angles or molecular shapes. And we're going to be talking about that using the concept of valence shell electron repulsion theory. Okay, so this is the main topic that we're going to have for today. And let's go ahead and break apart the word for what's called Vespr Theory. It's commonly called that. But when we break it apart, it's saying that it's the valence shell, so it's the electrons on the outside of the atom, that are paired and repelling against each other. Alright? And so what this theory is this is kind of a set of rules that determine the shape of the molecule. Because what's happening is that when molecules bond, those electrons are going to try and be as far apart away from each other as possible. Okay? And we have a set of rules that'll help us to go ahead and figure out how that bonding occurs. Okay? Or how that spreading out of electrons occurs, and it occurs at a regular amount, to the point that different molecules, we can predict what their bond angles are going to be because of the position of the electrons around that molecule. Okay? We're going to have to use a variety of concepts, and the first thing that we're going to have to do is Lewis dot structure. Okay? And we went over that one before, but realistically, the whole point of this Lewis dot structure is to see, where the electrons are in an atom. Okay? And, this is essentially going further here. This is an example of a Lewis dot structure. This is the Lewis dot structure for carbon dioxide. Okay? Notice that we have the lone pairs of electrons sitting right here. And those lone pairs, we didn't really think about them much before, but now they're going to play a much bigger role in the molecule, especially the molecular shape. Okay. Next is that we're going to go ahead and need to use the concept of the total number of groups. Okay. And we're going to be talking about bonding pairs and lone pairs. Okay. So bonding pairs, as a reminder, are going to be the amount of electron pairs that are shared within a molecule. Okay. Now, here we have phosphorus pentachloride, and the bonding pairs are the pairs of electrons that are in the bond. Because remember, this bond had 2 electrons in it. Okay. And then we have lone pairs. These are the pairs of electrons that are not shared with another atom. Okay. And it's usually the lone pairs on the central atom that we're going to be more concerned about. Okay? So in the one that we had from before, phosphorus has no lone pairs. But nitrogen here does have a set of a lone pair of electrons here. Okay? Because when we draw the nitrogen out, we would end up drawing the 3 hydrogens connected up, and we'd have 2 left over for the central atom. Okay? The next thing that we're going to need to be concerned with is the total number of groups. And this is going to be both our lone pairs and our bonding pairs. And both of these are going to play into the shape of the molecule here. Okay? And the total number of groups is number of bonding groups plus the lone pair groups. Okay? Bond angle and the angle between a bond in molecular structure. So for instance, in a tetrahedral molecule, these are 109 degrees around. Remember, this molecule is in 3 dimensions, so these are 109 degrees around. And then the last thing is going to be polarity. And we're going to have like a whole nother section on polarity too, because this is what really holds things together. Okay. Especially when we think about intermolecular forces or why water stays water, this is going to be because of polarity. So an atom is going to be considered polar when it does not have an even distribution of electrons in its orbits. Okay? So for instance, for this ammonia right here, it has this lone pair here, and it is polar because of this, because it has this one weird set of electrons that are all by itself right over here. Okay? And in general, if the central atom has a lone pair, we usually consider that to probably be a polar molecule. Nonpolar is when an atom has an even distribution of electrons in its orbits. Okay? So this one right here, this molecule right here, is considered nonpolar because all of its electrons are shared all around it, okay? And it has an even distribution. So it's nonpolar, so it's like perfectly balanced. So that's why this one would be considered a nonpolar one, okay? By observing these concepts, we can go ahead and determine the molecular shapes. And we're going to go ahead and start with the most basic shape here, and this is linear, okay? So linear, this is an atom, this is an atom, this is an atom, and they end up forming a straight line, okay? Linear, in general, has a total of 2 bonding groups. So for instance, carbon here has a bonding group to this side, and it has a bonding group to this side. And it doesn't matter if it's a double bond, triple bond, single bond. If it only has 2 bonding groups and a total number of groups that are 2, it's going to be a linear molecule. Okay? Now the linear molecule is going to have a bond angle of 180 degrees, which, should make sense. Like this molecule, this electron group, right here, the one that's right here, is 180 degrees from the other one. That's as far away as it can get from the other molecule group. Okay? Alright, this one is a nonpolar molecule because the oxygens that are on both sides of this molecule are both pulling on those electrons evenly. Okay? Now, if you had a different molecule other than oxygen here, then it would pull unevenly. And then you could think, oh, well, that's probably a polar molecule, but since it's both oxygens, it's a polar molecule. It's a nonpolar molecule. Ah. Alright, the next one is going to be trigonal planar. Okay? Trigonal planar is when you have a total of 3 bonding pairs and a total of 3 electron groups. Alright? So right here, boron trihydride has 3 bonding pairs and 3 electron groups. Therefore, it's going to be trigonal planar. And this is, the bond angle for this one is going to be 120 degrees. This is as far apart as these 3 bonding groups can get away from each other. Okay? So that's going to be 120 degrees. There's no lone pairs, and if you look here, all around, you have an even distribution of those electrons. Okay? It might be spread out across 3 different areas, but all around you have an even distribution. Okay? Therefore, this type of molecule is nonpolar. Next is a V shape. Okay? And you have, for this particular one, this is a 120 degree V shape. Okay? This is one where it has 2 bonding pairs, 1 lone pair, and you have a total number of groups of 3. Okay? So what's going on here is that we have this lone pair group here. Okay? And this lone pair group is affecting the bond angle of these right here. Okay? Because this lone pair that's over here that we can't see is affecting this bond angle. Alright? So it's affecting this bond angle and making it so that those other molecules are trying to get away from this one right here. Okay? And that's for a bond angle of greater than 120 degrees. Okay? You can almost think about it that a V-shaped one is essentially this one, except it doesn't have another atom attached to it. Okay? And, you know, to be perfectly honest, I don't know that I like this example that they used here. Let me see if I can. What's another molecule that has a bend like that? Okay. So, let's see. Oh, I can't think of one right now. Can't think of one on the fly. I'll show you one when we actually go ahead and do when we're in class. Okay. Now, observing the pictures, you should notice that there's going to be an uneven amount of electrons here. Okay. And you guys can see that there's an uneven amount even on the sides of the oxygens. But because we have some naked electrons on the nitrogen, this one is going to be polar. Okay. It has some naked electrons over there on the nitrogen, therefore it's going to be polar. Okay, which means that it's going to bond easily. Okay. The next shape is tetrahedral. And remember, this is supposed to be a three-dimensional shape here. And notice that it has the 4 bond angles coming off. Okay. Now initially here, we can go ahead and take a look and see, hey, there's 4 bonding pairs. There's 4 total groups. Alright? So without even going into the next one, this one seems like it's very evenly distributed, that the electrons around that central atom are evenly distributed. So we would expect it to be nonpolar. And that's what we see here, that it ends up being nonpolar. And the angle between these ends up being 109.5. Okay? And it ends up being that angle mainly because, you know, it's in 3 dimensions, and that's how they spread out as far as possible. Okay. Next here is trigonal planar. Now notice this one, we could already, or trigonal pyramid. This one, we can already see, hey, there's something funny going on here. Why is it raised up above the ground? Okay. And in fact, it kind of looks almost like a tetrahedral without the top one. And that's exactly what's going on. Here we have 3 bonding pairs and we have a lone pair. And the lone pair is forcing all the other ones down. Okay? And it's forcing it down just a little bit more, which is why we end up having a bond angle of 107.3. This one ends up being polar because these electrons right here are going to be participating in bonding. Okay. Next is V-shape, and this is what I call the 109.5 one. And V-shape, this one has 2 lone pairs and 2 bonding pairs. And these 2 lone pairs are going to affect the shape even more. Okay? And the lone pairs, if you think about the lone pairs, they're actually pushing down on these other bonds. And because it's just electrons and they have no protons to help spread them out from another atom, they're actually pushing down even more. Okay? So this is an example of a water molecule, and water ends up having a bond angle of 104.4. Okay? This is for bond angles less than 109. Okay. This one is definitely polar. In fact, water is one of the lightest elements that we have regularly in the universe, and it still has a melting point that's relatively high compared to other objects. And the reason for this is because of its polarity. The next one is trigonal bipyramidal. Okay. And this is going to be a case where we have 5 bonding pairs and 5 groups. Okay? And notice that we have no lone pairs on this central atom, so therefore we would expect that this is going to be non-polar. Okay? Next we have octahedral, and this one, even just taking a look at it, we can say, hey, this one has all of its charges spread out evenly. This one's likely to be nonpolar. Octahedral, we look at it closer, and hey, we have no lone pairs, bonding pairs of 6, total groups of 6. Everything's spread out fairly evenly. Okay? We consider it nonpolar. Okay? And these are supposed to be practiced, but we're going to go over them in class here. Okay? That's going to close us out for valence shell electron pair repulsion theory. I hope that it gives you a good basis that we can go ahead and start off on. And remember that this is kind of just more of a lazy way to think about shape and be able to figure out whether or not something's going to be polar. And from there, you'll be able to go ahead and tell a whole bunch of the intermolecular forces that are involved. Okay. So I hope this explains it well. And as always, remember that when you get the chance, be lazy.